Okay, I'll just quickly restart the session. It's around MyRocks. It's basically a Facebook internal, Facebook's own storage engine based on LSM trees, as compared to InnoDB, which is a very, very popular storage engine, in fact, used by majority of the people who are using MySQL. Facebook basically replaced InnoDB with its own LSM-based database storage system. We'll see why in just within this session. And before going into it, let's basically deep dive into what storage engines are, storage systems are. So database storage systems, again, yeah, fundamentally database is a stateful system. So it requires quite an optimized way to store the data that people access, that whoever the clients access, which is fundamentally the job of the database, right? To kind of provide the data in a seamless manner. And considering the amount of data that now increases with time, as well as the requirement of data overall within the databases, storage systems need to be really be efficient, fast, performant, and also durable in general. To follow the principles of MySQL as well, what MySQL kind of guarantees in terms of asset properties. So it's quite important. MySQL allows, like, MySQL is one of the biggest, in fact, relational database across maybe like multiple years, I would say. Postgres is definitely something that's been getting more and more popular with the new feature set and everything. But MySQL has been like really crux of one of the very, very foundational databases and very durable databases that people kind of rely on. A lot of systems rely on. Facebook is one of those systems that people use heavily, still relies on MySQL, not the traditional MySQL that when you kind of create a new server yourself with a MySQL installed, it's based on a different storage system than what Facebook uses. But yeah, MySQL is kind of where the flexibility offers is that you can kind of switch the storage system. And MySQL itself, in general, or like the database kind of design itself, doesn't follow like a distributed system, but like there's no situation where in scale you wouldn't want your system to be distributed and scalable and like across multiple regions and all of it. So with a cluster that that my Facebook uses, and in fact a lot of MySQL based systems, you would need to kind of prioritize at least 2 out of 3 items in the CAP theorem. And CAP theorem is basically what is also shown on the slides, is consistency, availability, and partition tolerance, and kind of provide at least 2 of it to guarantee performance and availability and durability and all of that. In terms of storage systems, again, InnoDB is one of the very much popular, or like I would say default, in fact, storage system that MySQL comes with. And it prioritizes, like, again, the whole fundamental durability aspect. It prioritizes really heavily, but it again struggles with partition tolerance and distributed settings without some additional help and tooling, which a lot of now new age systems provide. Even we're using InnoDB, which is Aurora-based systems, and new age MySQL distributed systems. And I guess there are a few of the other products out there that also provide this kind of offering. So yeah, storage systems as on the scene, like, requires management, retrieval, and storage of the database, the data. So like, just thinking of 2 kind of different blocks. There is an application layer, which kind of consumes a query. You pass in some query, SQL query, and we'll talk about SQL, of course, because this talk is basically about MySQL and how Facebook uses SQL and their own storage system to optimally handle their traffic, right? And we'll come to that. But basically, fundamentally, MySQL is an application, has an application layer. From a database point perspective, it's an application layer. And then there's a lower level layer, which is storage layer, which handles all the storage and writes on the disk and memory back and forth. The clients basically connect via, of course, as a server with the query parsing, query optimization, analytics, all of it. And then all of that boils down to a very fundamental crux of the system, which is the storage system that kind of is where MySQL shines, is that you can plug out one of the storage systems that it offers and plug in another one, and also kind of follow the same rules and set of things that MySQL offers, with an additional benefit of having your own storage system, or like your, or whatever storage system is preferable based on your use cases, which is where Facebook came into play in terms of switching their storage, switching the default storage system, and we'll see why they did it. But before that, we'll first need to understand InnoDB itself, right? Because we need to understand InnoDB itself to understand kind of get the perspective of why Facebook didn't like it, like for their use cases, for their scale, or for whatever reasons, right? And they were serving traffic like significantly for past whatever few years that they started with, but eventually with enough scale, and as we know, Facebook scale, uh, they definitely did had some bottlenecks. But like we'll deep dive into what InnoDB offers internally first. InnoDB is the default storage engine, as I mentioned earlier. It offers transaction logging, like WAL techniques, which if you don't know a lot about, like WAL or like write ahead logging is fundamentally a fundamental aspect of any relational database, or in kind of database that offers durability. Um, Again, to ensure integrity, durability, all of the fundamental aspect of a database, and a stable database system. Yeah, it also sets some predefined rules for us being ACID compliant, to kind of do locking based mechanisms and all of it, to kind of maintain the database and integrity of the data that people write into, and also make sure that the data doesn't get corrupted. It uses undo and redo logs, which is basically WAL is a strategy, and undo and redo logs is kind of an implementation of WAL. WAL strategy. So it kind of breaks down. Let's break down InnoDB into kind of 5 fundamental blocks of systems. Which one is buffer pool. Really important in terms of performance. Without this, you wouldn't be getting the performance that MySQL offers currently, in terms of latency, in terms of reads, in terms of scalability for a cluster as well. Very important. Log files, again, as I mentioned earlier, which is like one of the unit of for durability aspect. And also in some aspects, it is kind of important for performance as well, and we'll see why in a bit. But like, I will not go into too much details, but basically it gives, because log files are sequential, right? Like every you just append only, right? So that you just consider that why sequential versus random IO. You really need to understand random IO is slower than sequential IO. Fundamental fact is that each disk or anything that you use, SSD or hard drive, it's divided into blocks, and those blocks, access for each different blocks across the disk and across flash storage as well, is fundamentally slower due to physical limitation. And that's why log files are much faster. And you'll see why sequential IO basically is very important across the Facebook use case as well. Then there's data and index files, basically that the fundamental data, right? The fundamental data is stored into table spaces, and then it goes into like structure, which is we call B plus tree structure. That is where the kind of key aspect of data storage comes for InnoDB, and for a lot of other database. In fact, not just InnoDB, B plus trees is used in even in Postgres or even in other Oracle database systems as well. Log buffer is temporary storage for redo logs and log records, because the redo logs or like the WAL records basically are written to disks. So again, to have a bit more faster writes and faster performance, you like MySQL adopts this log buffering technique to use it more in memory writes as well. Then there's change buffer. It's again an optimization technique. Change buffer is basically keeps secondary indexes in a change buffer in memory until it's required to be written to disk. So it avoids writes, and then you'll see like the whole what I'm saying, basically everything comes down to avoiding as much possible IO as possible. Again, fundamentally, disk is slow, memory is fast. Reduce as much disk access as possible without, of course, affecting your application's requirements, right? And so yeah, that's where InnoDB's like internal blocks, like I would say, kind of how it's structured. This is a bit of like a visualization of how it looks like. Redo logs, as I mentioned, also written to disk. Table space is basically like a logical unit of data being stored on disk in terms of files, like IDB files for MySQL, .idb extension. And those files have blocks of data in pages. Internally, it has pages, which basically has B plus tree structures, structure being there in the file itself to, again, have the access for the data, faster access for the data, and retrieval and of course writes. And it provides that the faster access via the B plus tree structure, which is basically, again, the logarithmic access times that it provides. And we'll go into B plus trees as well a bit more. And yeah, so basically fundamental data structures in InnoDB, as I mentioned, B plus trees, double write buffer. Again, double write buffer is again more of an optimization for durability aspect. Undo logs, redo logs for wall techniques, for wall strategies, and for MVCC, as we'll see, because it requires, for MVCC, it requires a snapshot of the current state of the database as well, or the table as well, that's being read fundamentally for faster access, faster reads. So that's where also undo logs come into play. B plus trees. Okay, so B plus trees, as I basically was saying earlier, it's a balance tree, and it provides like a kind of a logarithmic access to the data, right? Logarithm access, by logarithm access, I mean is in logarithmic time, you can access the data that you require, access the keys that you require. And B plus trees is fundamental data unit, data structure for MySQL InnoDB. Fundamentally uses leaf nodes as the navigational nodes, and sorry, non-leaf nodes as navigational nodes, and leaf nodes as the data nodes, where the actual data within that block is written as, like, the pages are written, and those pages contain multiple rows of the data. So if you have like multiple rows, those are the pages, those are the rows that basically are stored in the leaf nodes. And there is some bit of optimization with the leaf nodes and how it's structured, but basically you can see like it's a balanced tree, and it allows for much faster access than, let's say, you were to have your own. And this is basically a serialized on disk, right? So if you were to kind of assume that you would just have a hash map with all the data, you cannot fundamentally keep that in memory, or even it on the disk. It's in fact not as fast. Like, you'll have collisions and all of it. So it fundamentally has a trade-off with the amount of reads and writes that you would do. And yeah, so that's by B plus trees, and I think it's a fundamental data storage for all the indices as well. So if you have an index, primary index is basically in MySQL, it's cluster index, which means that the primary index is essentially the data itself, as in B plus trees, and leaf nodes would contain the data values itself, the rows, essentially the pages and the rows. And with secondary indices, it also creates a B plus tree, but the references to the data is via the primary key and not actually the data, just to not, of course, duplicate the data, right? So that's where it kind of that's how the MySQL based InnoDB based structure looks like. And transactions with InnoDB B plus trees, as I mentioned earlier, like with MySQL and InnoDB, it provides the fundamental system to allow for locking, latching, and asset being asset compliant, and has different techniques to do that. And because if you think about it, like fundamentally, the rows are not like as is not the fundamental unit of storage on a disk. It's the page that's being brought back and forth from memory to the disk, and basically the operations around even on CPU as well. So so that's why InnoDB has a bit of optimization in terms of implementation to do this row level locking, which is like offloaded to the storage system, which is InnoDB via MySQL. Yeah, and in terms of optimizing this, as I mentioned earlier, with everything database does, the biggest effort to optimize whenever you want like write your own database is to try and reduce as much disk I/O as possible, reduce as much disk haul as possible. Again, fundamental factor is disk is slow, so that's why like in InnoDB, they have multiple techniques to kind of at least avoid disk I/O or optimize for disk I/O in case there is a requirement of a disk I/O. So it does prefetching of non-leaf nodes or the navigational nodes, and like also prefetching of leaf nodes. What does prefetching mean is when there's some operations like range queries or kind of where in clause or where clause queries or anything like that. The keys that being brought into, if assuming that's a primary key within that B plus trees, it would find that key, and it doesn't just fetch the one particular non-leaf node, right? Because considers the fact that it's structured and the data is only on the leaf node. It needs to fetch multiple non-leaf nodes in memory first to do these operations, and then find out the leaf node that is on the disk, and then fetch that as well. And in case of, let's say, range queries, you are not just fetching one leaf node because the data is spread across multiple leaf nodes. And that's where prefetching and having pointers to sequential pointers to multiple leaf nodes helps. And that's where my InnoDB also leverages that and kind of make sure that range queries are significantly faster. And very important, range queries are one of the very important things that you'll see how Facebook also struggled with the new solution and how they have kind of solutionized and kind of a very beautiful solution as will go. Of course, now we'll be talking about B plus trees, and it's great, right? Like it works really well in majority of the cases, but we haven't spoken more about how the practical implications of writes on B plus tree looks like, right? Because as I mentioned, if you see, basically it's a one single leaf node, then it kind of needs to be broken down as we write more and more data, because since each node, I mean, I probably missed this, but like the fundamental fact is the data within the single node is sorted. So because of the login time guarantees, it needs to be sorted. So the binary search needs to perform in login, basically. That's why whenever you write more and more data, the keys needs to be fragmented as well. And also every time you write, or every time when the writes happen on a B plus tree, it also has side effects, right? And those side effects are not clearly visible for like from a user's perspective, client's perspective, but those side effects are like clearly impacting and kind of visible on the disk, because when you write, when the key is something that is not within the same node, and it needs to kind of divide the node into sections or multiple sections, that is when there is an additional operation that needs to be done, like the node splitting happens, the cascading split happens, because once the node splits, then there is another kind of lower level node also getting split because of it, and that triggers like a multiple operations on disk, and it's basically more resource intensive operation as it goes. And just kind of once your one single write kind of caused this, and let's assume that you're writing heavily, this is and not just one single operation on the disk or for CPU. Basically, there's a lot of back and forth happening with the data, and there's a lot of changes that happen within the structure, and all those changes needs to be put into memory first, kind of run those operations, and then put back to the disk, which is definitely not fast, right? As the other operations as compared to. So these kind of things and not visible to it, and what it means is that every write can trigger multiple writes. Like it's not a one single operation, like when you insert into or when you update, you would assume that's like one single query that you're running for one single key, but that doesn't happen on the disk or on the lower levels, on the storage level. And that is where B plus trees kind of limit, like they're limiting themselves, like they get limiting the client applications and the resource utilization. They kind of increase the resource utilization, so it limits the scale. And if you are writing more and more data, you will basically fall into the same trap as what Facebook did. Facebook kind of also had to fell into the same trap when they realized that it's not handling the amount of rights Facebook needs. And that rights are essentially, just think about me, you, everyone else using Facebook with likes, share, whatever that we do, commenting, all of it. And all that data is basically returned into a user database that they have, which is MySQL based. And if considering the fact is not just me, but there are like millions and in fact billions of people using Facebook every day, it's just not scalable. Even if we have kind of multiple partitioning, sharding techniques, and all of it, you could try squeeze all of that in, and it becomes more and more complicated. In fact, to set that up first of all, and even if you like, let's say, find an ideal solution, ideal sharding technique and sharding system, it's very difficult to maintain that kind of scale as a number of data increases as well. So that is why, and there's another problem with B plus T is fragmentation with the deletions, and like if the B plus tree becomes imbalanced or unbalanced, so it becomes non-uniform. So you would kind of want your performance, the read basically gets impacted because of it, and that's why it's not the most ideal structure, and that's why it requires kind of constant management and constant rebalancing internally, and that's why the fragmentation occurs. Um, and it leads to, again, inefficient storage space. Like you'll use more storage because of the fragmented data, and because of there's like a lot of metadata requires for each fragment as well. So each data being distributed, each B plus tree is distributed as well. So that's why it's important to kind of identify kind of identify this problem as well. And like fundamental fact with B plus tree is random IO, right? Like if you think about it, it's not sequential. If the loads are there, it's a pointer to the next node. On the file, it's an offset. That's not a same offset. It's not like each and every single, assuming that a file is like just think about it in terms of visualization, is like lines. It's not like the next line is read again when with a node, and there's another next line again read with a node. It might point to a fourth line or a seventh line or 10th line, which is the offset basically of the file, for the file system that Linux, let's say, uses, right? So it's not sequential. It's random, and random IO, as we discussed earlier, is slow. Uh, IO is slow, and then random IO is even slower. So. So that's why, like, and as I mentioned, problems with partition shards on MySQL clusters, like there were some scaling challenges. Sharding complexity becomes more and more difficult, like logical sharding, partitioning, or it requires. It's like you're trying to solve a problem that will never be solved, kind of, more or less, as the scale increases, and you just have to kind of start thinking in first principles rather than trying to kind of patch this problem, which can, in fact, only increase as the scale increases. There's also cross-region latency, which data spreads. So yeah, there is like multiple other aspects of Facebook's use case that is not the most ideal. InnoDB is not the most ideal storage system. Or like even going back, MySQL itself, like with default InnoDB, MySQL itself was not the ideal solution. But then what would they do, right? Like just think about, again, you being a part of the Facebook engineering team. What would you do in this kind of challenging situation where your system is not able to basically handle the business, right? And that's where you would kind of come up with a solution that doesn't impact the business, first of all, but also allows for the business scalability, and builds a flexible solution that allows for like few further scale and future business requirements as well, without costing engineering resource, right? Like, or additional resource to migrate to a, let's say, new database system or altogether, which is in its a big task itself. Writing the client application, changing the code, changing the SQL, maybe SQL to maybe, let's say, different queries system, like, let's say, MongoDB or like Elasticsearch or something like that, requires a complete rewrite of client systems or client applications, which is a daunting task, coming like to a task which with having Facebook like applications altogether with so many features. So Facebook's UDB is essentially what I mentioned. It's a user database with all these likes and comments and user interactions, and all of that data um, is being written to that database. And how would Facebook come up with a better solution, right? Like, um, it has multiple, as I mentioned, multiple sharding, kind of managing social graph for all the user database, associations with people. So, excuse me, it requires some specialized architecture, and that's where Facebook does use like write through caching system, which they call tau, which and then there's like a pub subservice wormhole to kind of share the data across multiple zones replicated zones. So they have already have some solutions in place for like replication, but the fundamental problem and fundamental fact is that the writes, that the amount of writes that they do is and then the amount of storage space it's required for, let's say, one single region, it's significantly high. The resources usage for the amount of writes that's happening and amount of um, um, API access is being happened on the server, on the database server, it's significantly high. So how do you solve for that? How do you solve for this amount of storage being used? And this fundamentally, if a lot of storage is used on the disk, it also essentially impacts your memory, because now you need more memory to handle a lot of data being pulled into memory, and that requires you to kind of vertically scale even further. And like there's a limit that you'll basically will reach even faster, right? Than let's say a more optimized solution, which Facebook then goes into. So all that blabbering that I did comes down to the fact that B plus tree is not the most optimal fundamental data unit that Facebook's use case that handles the Facebook use case, or that can manage Facebook's use case, right? Like with writes. So B plus trees is not the most optimal structure for writes, the amount of writes that Facebook does. And that's where the log structured merge tree comes into play, which is the LSM trees, is very popular, very popular, in fact, data structure in NoSQL databases. And now we'll see that it's also in a SQL database, which Facebook basically built for themselves. This is the LSM trees are like, it's not one single data unit. It consists of multiple like structures, and it has multiple data units, which is one is mem table, which is the memory table, which has which in case of Facebook's LSM-Tree implementation, which they derive from RocksDB, which is again their own NoSQL based database, key value pairs database. It is a skip list in memory that kind of holds all the writes. So let's say you, me, there are 1,000 others writing, like liking a post. All those writes goes to the mem table in a skip list, and until and unless it reaches the amount of like a threshold in terms of the amount of nodes, in terms of the amount of key values, it would then flush to disk, and not before that. And that is where the write amplification problem reduces, right? I wouldn't say it gets solved, of course, but it reduces significantly, right? Like on let's say on a SSD based system, this is in fact quite better than before, where the writes were even dirty writes in case of MySQL, even dirty writes get written on disk in some places based on your configuration. But so it's in this case, like, you don't do that. You just write to a memory and then return to the client saying that your writes is done, basically, right? And of course, you'll kind of think this as well, like it's not durable. What happens when, let's say, a system crashes? Yeah, it does also write to wall, as in, like, wall is not just used in like MySQL InnoDB. It also it's being used in this LSM based structure, because for durability aspects, in case of MySQL, which is what it guarantees, you would need to kind of make sure that in case of crash, at least you can replay the data back and get the do not basically corrupt the data that you've written, or like reduce the chance of missing out any on the data that was written. So yeah, basically memtable is the first kind of write unit that happens. And val logs, like we're going back to val logs, first of all, val logs are sequential, so it's much faster writes, right? So you don't kind of in terms, even for disk itself, it's not slow, it's not resource intensive. So that all of that kind of gets solved, and it's all kind of encoding techniques, multiple encoding techniques with val logs, make sure that it's very much optimized for the amount of writes that happen on the logs. Um, Coming back to the mem tables, like with the skip list, it kind of is in memory. And then after a flush happens, this is where the another interesting structure comes into play, which is SS table. And this SS table is kind of immutable, not kind of, sorry, it's immutable. And this immutable structure guarantees that that there is no in-place update that happens. And in-place updates is random, right? That's random IO. So that's why this is where LSM trees are leverage this sequential IO for on disk, and that kind of reduces the chance of random IO, and that basically helps using less resource on the on the system altogether. And on the disk as well. And when I say disk, I mean also maybe in like it could be a hard drive or SSD. So core components, as I mentioned, like this is the mem table, the sorted string tables, and SS tables are basically sorted as well. So the keys in SS tables, like there could be multiple keys because based on the mem table, let's say there are 10 keys being written to the mem table. The flush happens, it creates only one single SS table that has all the keys in sorted order. And this is really important again for the sorting is basically used for, of course, the reads that happen later. And then there's another process called compaction. So we saw that there are multiple, every time you write, every time the mem table flushes, it creates a new SS table. Now, with let's say key name, and there's like the same name key being updated every time, like column name, and then there's like the same key, let's say my name, and you would still create like multiple values of that, right? So you need to kind of compact the data back to reduce the amount of storage that is being used. And also like for read perspective, because now you have multiple versions of the same key. Of course, it's versioned. You can kind of find the latest one and then kind of return to the client, but it still uses like an additional storage and additional reads that are required. And this is something that where the LSM trees, in fact, is the disadvantage of LSM trees, like the pure without any optimization LSM trees come is like the reads are slower. And this is where like again we'll go into details of how it's optimized. But in terms of space usage, like since there can be like blocks of data being written, you can kind of with pages, they are fundamentally fixed size blocks, so you cannot further optimize for it. Even if you compress the data to let's say 5 KB, even your page size is 8 KB, it would still use 8 KB in memory versus on storage. Versus let's say in SS table, it has this benefit of using like compression, and it can kind of reduce the storage altogether to the actual data that being used within that SS table. And SS table essentially does contain the actual key value pair. The key being, let's say, in your case, let's say if you have one single column, which is your primary key ID, integer ID, then that's the key. And the value is basically the list of like, there are different encoding techniques, but basically the column, all the column values are stored in that particular block of SS table. So it's like a multiple key value pairs within the same SS table. So like think about it as multiple rows essentially. So yeah, there are multiple ways, as I mentioned earlier, to improve read performance, and we'll go into details, in fact, more on how, in fact, Facebook achieved equivalent amount of read performance without like with increasing with reducing storage cost and reducing storage usage and resource usage altogether, without also increasing CPU usage. And we'll see why CPU usage was very important in this case, because with compaction, with other operations with LSM trees based structure, and I'll give you one of the examples that in fact I personally faced in my own work, and we use Elasticsearch quite a lot, heavily in fact, in our search-based systems. And it also uses this kind of a different version or different variant of LSM-Tree. It has an in-memory buffer, writes to disk after the buffer has been flushed, and based on a refresh interval that we've kind of configured, and then it writes it into a segment. And essentially, it's kind of sounds similar, but it has a different index structure because Elasticsearch is optimized for key text-based index structures, and don't need to go into too much details. But essentially, with each write, new segment is created, and there is like compaction or like segment merge operation. In this case, we call it compaction. In case of Elasticsearch, it's a segment merge operation. So those segment merge operation requires to bring all the segments back in memory, merge it in, find out like what's the merge technique based on like the data itself and all of it, and then kind of compact the data. And now you have a kind of compacted data, which is again faster for read perspective, but it still requires a lot of operations for the system itself, right? It's an asynchronous operation that can stall your IO as well, that can impact your other operations as well, and which I have seen, in fact, practically happen much more recently. And we have kind of a lot of optimization solutions around it, which is caching, and which is you kind of think about a very, very simpler solutions as well around it. But yes, so these kind of things kind of occur a lot with more or less a silent process that you are not really clearly, like you do not have visibility on as a client or a user of the system. And that's where the optimizations that Facebook brings in to their own solution, which is the MyRocks on top of RocksDB, is really, really critical, and even for industry-wide optimizations, in fact. Which is Bloom filters. There's like some rate limiting and compaction, tiered storage systems all for reads purposes. So only levels that have the latest values are being kind of promoted, and so you don't need to read the old values, and there's a little lower levels. And we'll go into too much more details as we go into more slides. And if required, you can of course read more. I'll share all the details and the references as well. And yeah, so LSM-Tree also with sequential IO, right? Like I haven't in fact mentioned it over here, but sequential IO is also one of the very core features of LSM-Trees, and that helps with reduced IO, or like reduced cost of IO, I would say. And that's and also with in terms of the SS table itself, it can be compressed in further, so that also brings more efficiency in whenever it's the SS table is pulled into memory for other operations, for key range operations or search operations or whatever filter operations, right? Yeah. Excuse me. LSM-Trees and okay, so as I was saying like earlier, LSM-Trees are great and they work really well for the write heavy operations, but with each writes, it is sequential, but it is costly later on, more or less, because it creates multiple versions of the same key. And then it requires the system itself requires the storage system itself requires a synchronous operation to kind of compact this or reduce this this data. And that's why the stale data versions is being kind of cleaned up as we go. Compaction happens more or less. Every time there's a read, you kind of read more keys, because now you'll have to kind of make sure that the version is not the key in the key itself. So you need to make sure that you'll kind of read the latest version. So if you're reading more, if you want to read the latest version, you need to read the same key multiple times if it's in the multiple layers, right? And this again with leveling and with other optimizations, you can kind of reduce, but it's still visible, more or less. Yeah, so going to the limitations, like it requires more CPU, more memory, and with RocksDB itself, with the compression techniques that I mentioned, Facebook basically targeted their storage, the amount of storage they use, and that's why they require more compression. And with more compression, it requires more CPU cycles, right? Like you would want to kind of, when you serialize back, when you compress back, all of that requires more CPU cycles. So that's where with the amount of compression that Facebook RocksDB kind of possesses, and kind of Facebook tried to do that, they did reduce their storage, of course, but it requires more and more CPU. And we'll see that Facebook also, in fact, optimized the CPU usage and made sure that it's almost equivalent to the previous system, and also optimized storage altogether. So trying to bridge the gap, basically. In terms of forward and backward range scans, like an order by clause, like when you if you think about it, um, the SS tables for, let's say, one single key value pair, like one single column A and B column, um, it's sequential. Its forward scans are much easier. Like you could just, because it's sorted, you could just basically kind of order within the like the forward within the each forward access or forward iteration, and it's much more simpler to get. But in terms of reverse iteration, it becomes more, essentially multiple operations on that, because you cannot just you don't have that access to the last value and then kind of come back. Like it's not easy to do that. That's where there are other optimizations around that, where the reversal of the bit, the byte itself for the key happens early on for those optimized cases where you would want order by descending or something, like let's say timestamp or something. And that's where also Facebook optimized for their own use cases for those reversal operators, or like order by descending operations. They also kind of like they have this key comparisons I mentioned earlier. They have kind of using multiple versions of keys. They need to come kind of read through multiple versions of the keys as well. So that is more and more key comparisons, right? So with each key comparison costing some value, which is serializing the key or deserializing the key back, and then checking whether, let's say, ABC string matches the ABC string or XYZ string. If it doesn't match, what to do. But this is costly as well. It's more CPU essentially for the deserialized and serialization bit. And that's where Facebook also comes up with different optimization around key comparison. And that also, in fact, helps within range queries as well. Range queries, what range queries, what I mean by range queries is basically where A greater than something, A less than something, and like those queries that you fire in just simple SQL terms. Tombstone management. This is really important. I think we probably missed more or less, but a delete in LSM based system is again immutable SS table, right? So since the SS table is immutable, you cannot do in place update of an existing key. So how do that? You do that. Basically, you have a key, let's say name, and as a column name, and let's say it's Dharin, my name as a key. The delete is basically a logical kind of a SS table value itself that kind of provides that this key is deleted. You cannot, this is the newest version of the key and it's no longer existing. It's basically kind of a logical indication that this key is deleted. However, that the data still exists somewhere in a different level. It's just that this kind of indicates to the client that this is deleted whenever the read happens. And this is another kind of aspect of why it's kind of the offline stuff or more asynchronous stuff impacts overall resources of the system, and why it's kind of LSM-Tree is not the solution, like just like a put in that solution and now you're kind of solve all the scalability aspects of scalable problems. Just like with any other solution, NoSQL is not a solution, SQL is not a solution. You kind of have to kind of work around your own use case and identify what's the trade-offs that you are what trade-offs are you considering within the solutions, right? And Facebook did try to, of course, try and optimize for all of those cases and made sure that, because they're going to open source, they have this open source solution. They want to make sure that not just Facebook is being is like using advantages of the system, but also other people who have the similar problems in terms of their own system can leverage the optimizations that Facebook did with RocksDB and MySQL. So yeah, so as I mentioned, to address the limitations previously mentioned, they for CPU reduction they did mem comparable keys. What it basically means is that, and I'll not go into too much details of each. I'll probably have more details in for few of the optimizations. But with mem comparable keys, you basically do not compare the actual deserialized value of the key, but more or less compare the encoding, the byte value of the key itself. So you don't need to do this transformation of back and forth in terms of the serialized and deserialized version of the key. So that's faster, in fact, because again, see less CPU cycles. it's a more natural or organic comparison directly on CPU itself, in L1 cache or something, right? And reverse key comparator, as I mentioned, like reversal of like order by queries, descendant queries, it's not as straightforward as, let's say, B plus trees, because B plus trees you can just basically go to the last value. It's like a log n operation again, and then follow an in order traversal to kind of find the reverse order of the range that you were asking for in SQL. Then there's faster approximation for query estimation. This was again with each queries with InnoDB as well, and like it provides analytics support to kind of identify which is the best index to use, what's the best query estimation plan to use, what do we need to use the buffer that already exists, the page existing there, or should we go to the disk, all of that. So those kind of fine-tune optimizations that's required for estimation, which MySQL application layer requires. They did some faster approximation to reduce the time to process the query and identify the best path for the query. Read latency performance. Bloom filters is really interesting data structure as well. Like it is a probabilistic data structure which kind of tell you like it might be there, but it guarantees tell you when if it's not there. So for example, if you ask for a key X, if the Bloom filter tells it's not there in the underlying storage, wherever you're storing, it will definitely not be there. But if there's like a yes and no kind of solution that could be there, so it could, in some places, like it could be there in the underlying storage. If Bloom filters is like with probabilistic, it says that it could be there, then you potentially have it on the underlying storage, but not necessarily. Like sometimes you might not have it. So it guarantees the case when it's not there, and that's where you would reduce the chance for any kind of negation operations to go to the storage system altogether, and just are much faster in terms of kind of getting the access of the response for that particular scenario where you have a negation query. Yes. Okay. Sorry. Yeah. So in case of, let's say, like as I said, key operation, which is where key equals ABC or something, I mentioned like it uses mem comparable operators, and I've like given like a very simple sample Python script that does it. But excuse me, it uses I just had dinner, by the way, but yeah, sorry. It uses mem comparable key format to encode the MySQL data, and like it's much faster. It reduces the chance, like reduces CPU cycles, because it doesn't need to deserialize into the format and like compare two keys, A, B, C, and X, Y, Z. It can just do it on the kind of more on the binary format, and also with case insensitive values as well. It does apply similar techniques and kind of converts the existing key into a case, a lower case, and then kind of compares on the uh, the byte value itself, or the bit value itself, right? And this is much faster, as I mentioned earlier. Order byte is, I think I was also discussing the same in terms of reverse. Facebook has this reverse iteration kind of system, and they only use it like basically creates a new SS table with a reversal key value. So let's say in terms of timestamp, let's say timestamp is your one of a key in secondary index or something. There's another SS table, or which is essentially, or another LSM tree, for which it has a reverse of that particular key timestamp, and then reverse in terms of the bitwise in terms of the bit space or hexadecimal space. And that kind of allows you, because it's the reverse of that in that space, is essentially the opposite order of the case when it's actually not reversed in a sequential manner. So that allows for like a forward look, even in case of when you're kind of trying to find descending, like running a descending query or descending order by, and that is much faster, sequential as well. And then you can of course reverse it back when you get the fetch the results. But essentially, this is what and you can kind of like Facebook basically fine tunes for the operations that they require for this order by, and create the index based on that. So each in the secondary index is basically based on, let's say, if you want to have a descending thing, then it creates an LSM tree with reversal order. And yeah, I'll of course share the references to all of this. And if it becomes because of limitation of time, we'll probably not go into too much details. But basically, it's a very interesting technique to reduce this gap between forward and reversal order in terms of performance. Um, yeah, with the range queries, as I mentioned, there are like probabilistic data structures, Bloom filters, that two-level indexing. So if SS table contains, like, just to identify which SS table contains this key, instead of going to like even sequentially scanning the SS tables, you will have like two levels of indexing. So you kind of provide much faster access to the SS table, and then um, do the range queries from that starting point. And now that's much faster, like just sequential, right? There's prefix Bloom filters as well for like very query work for social graph workloads specifically, where there's common of share common prefixes, so you can kind of have more sequential IO for those common prefixes as well. And then Bloom filters kind of allow you for faster access to those SS tables as well, and like not going to the SS table. I mean, like with Bloom filters, in case the prefix doesn't exist. Um, and yeah, there are other operations, there are other optimizations that Facebook in terms of the white papers they have discussed and mentioned. I want to keep like last 5 minutes maybe a bit for questions. So I'll just be more quickly go. With migration, since the clients didn't change, clients didn't was kind of transparent to clients. They built this migration technique with the writes being solved to both of the database servers, the InnoDB based servers as well as the LSM based servers, and then like slowly and gradually they increase the traffic to the read traffic as well to the MyRocks based servers, or LSM based servers. And yeah, that was one of the interesting, very complicated migration plans for considering the amount of scale Facebook has, zero downtime basically. So yeah, it's an engineering challenge that they were able to. This was basically, they already did this in 2017, by the way, and they were able to achieve this quite without any downtime. So it's a kind of an achievement. Um, and like just kind of brief summary of practical outcomes of RocksDB or InnoDB. Like they have random with MyRocks, it was sequential. So that's one of the fundamental learnings as well for us as well as for Facebook when they try to identify the bottlenecks during their system, within the system. With write consolidation, regex happen more frequently due to that, like the fixed page structure as well. And each write operation can potentially amplify multiple operations on disk. With MyRocks, as we mentioned, like a lot of IO happens in batches, and kind of you see a trend where like batching in general overall, when you do batch writes as well, even with a simple DB structure, it's much more efficient because again you reduce multiple IO, like you do more memory and IO operations in bulk, and then multiple memory and IO operations within the span of let's say a few seconds. In terms of read and write improvements, performance was kind of equivalent because they made sure that they don't want to impact reads. So again, fundamentally, because that's one of our, of course, the primary use case is reads, right? So they had all these optimizations that I mentioned earlier with Bloom filters, with reversal range queries, with function management, like so all of these over here. So they made sure that the reads are not affected, and also CPU utilization, like with in terms of compression. They use less storage, and I'll share, like I'll of course have the link to that, but you'll see like it's basically 62%. They reduce the instance size of their single server by 62%, which is like amazing. So, and without costing any performance or more resources in terms of CPU, which is again requires more complicated solution, of course, required more complicated solutions, but in the end, they achieved it and made sure that it's open source as well, so you can kind of check it for yourself. In terms of like fundamentally, it comes down to the fact that there is like a big difference between B plus trees and LSM trees, and like you cannot just say one is better or one is worse or anything like that. Of course, it's a trade-off. We heavily use B plus trees based system, but our scale is not equivalent to Facebook scale. So it requires you kind of identify what exactly your use case is, but like B plus trees performance can degrade to scale with amount of writes, not reads overall. Like if you are okay with your replication lag, then it's fine with even like it has amazing read performance. With LSM-Tree scales better because in terms of IO, like in terms of writes, because it does patching. Uh, and as I said, right amplification, and in terms of use case as well, like you need to fine tune your use. You need to fine tune the system that you have in place for the use case that you're trying to prefer, instead of like just kind of forcing a solution to the use case that doesn't really match, right? So yeah, that's pretty much it in terms of I was a little bit quicker at the end, but I'll just leave 2-3 minutes for questions in case someone has any. And I'll also as I think as always, I will also share the slides it on I'll share my email as well. You can reach out uh, and also reach out on LinkedIn if you want. This is my email, and just feel free to kind of message me if you want the slides. Any questions? Thank you so much, Pawan, for being here. Did I? Okay, sorry. Yeah, this is my email. Just feel free to reach out and ask for the slides if you want, of course, or if you want to have kind of a quick chat or something around this. And if you're interested in discussing more of such systems and such solutions. Cool. I think we still have 2 minutes, so I'll just wait if you have any more questions, if anyone has any questions. I guess not. Thank you so much. Thank you for all of your time, and see you.